So I'll be talking a bit about the BAO reconstruction problem. I'm not sure if you covered that kind of thing in the school. So I have like 2 or 3 slides on that before we do it. And the kind of thing I'll be describing is, in the jargon, is called field level reconstruction, where you're actually trying to reconstruct all the particles rather than trying to reconstruct a statistic. I've also done some stuff on reconstructing just statistics. Some of that is recent work with Aseem, but because he's the chair, I thought I shouldn't push my luck and talk about it. So this is work that I've done with Farnik, who was a student at Penn and is now a postdoc at Yale, working with Nick Hill, and they'll apply some of this to DESI. The method has a long history that, so Roya was someone who worked with early incarnations of this. And she's teamed up with Bruno, who's done a bunch of the computer science hardcore coding that makes all this possible. If we have time, I'll talk about trying to understand some of the results from this, and that will use peaks theory, and that's work with Marcello. Yeah. Okay. So the talk is in 2 parts. I'll do the BAO first, and then maybe we'll have time for the peaks in energy. So a quick thing about motivation, then the method, and then the complications. Yeah. So the method is, we see spots in the CMB. That's a surface that's some distance from us. We can use the size of the spots in the CMB to do a geometrical measurement of the expansion history of the universe. And so the great thing about these spots is that the linear physics is imprinted in the galaxy distribution at later times. And so those spots have a distinctive pattern on the sky, galaxy distributions at different distances from us. These are circles with the same co-moving radius. They're different distances from us, so they have different angular sizes. And so in the sky, we should see this sort of pattern, and depending on the redshift of the galaxy sample we've picked, we should see these circles on large scales. And large scale is important because that means there's some hope that linear theory, perturbation theory is still valid. Yeah. So that's a quick cartoon, and the great thing is it's the same physics at many different redshifts, and so it's sort of a clean standard rod. That's the logic. Okay, so this was the animation that isn't going to work. This is a cartoon that was made by Nick Hill 10 years ago, where, so these are the initial conditions of a simulation, and all we've done is, to the initial conditions, we've added extra lower mass particles so that you can see the shell that represents this BAO feature. And then you run the simulation forward and you see the shell deform. And so it ends up being deformed to something like that. So the red circle is the initial, and the black fuzzy thing is the late time thing. And so the idea is that, to a good approximation, the radius of this circle has not shrunk over the 14 billion years from the CMB to the present time. Okay? And it has gotten slightly deformed, slightly fuzzier. And so that means that you've degraded what would have been a nice, reasonably sharp peak. You've degraded it into something a little more smeared out. And so a bunch of the BA analyses are trying to just reconstruct the spike from the current late time smeared out thing. Yeah. And so there's a bunch of algorithms out there trying to do this, and I'll describe one of them. So this one goes under the name of optimal transport. There's a beautiful literature that I don't have time to get into. It's a 200-year-old problem. And so the step forward that we're trying to exploit in this is the following. So we're going to try to reconstruct the initial conditions. We want to make as few assumptions about cosmology as possible in doing it. And so the assumption here is that the initial field was smooth. And so that's supposed to be generic to essentially all modern cosmology models, right? So the fluctuations that we see today are driven by the fact that the velocities are correlated. And so you take a smooth initial field and you make it lumpy. Yeah. And so that's what we're going to use. We're going to say whatever the initial points are today, they came from a smooth grid in the initial condition. And so the optimal transport problem then ends up being a problem where you just say, so I have a set of points which are clustered, and I have a set of points that's the initial grid, and I want to know which point went to which grid position. That's the problem. And so then you need a metric that describes the cost for moving a particle from one place to another. Okay. And that's just the distance in this problem. And so the Euclidean distance in this problem. And so you just want to find the set of distances that is minimized to give you an initial grid from the current clustered distribution. And that gives you your mapping of which particle is associated with which grid. Okay. In principle, this is just the combinatorics problem. You have n particles, n grid points, and you want to know which one maps to which. And so you go through all of them. Only you can't, because that's a really hard problem. And so you've got to do it more efficiently. And so the step forward that the computer science guys have is how to do this efficiently. And the way to do this efficiently is to no longer think of this as a discrete problem where you have n points being mapped to n grid points, but to think of it as a semi-discrete problem. And the semi-discrete problem is you have your endpoints and you're trying to map them back to a smooth field. And the way we're going to think of the smooth field is as follows. You could first make something that's called a Voronoi distribution. So a Voronoi distribution is you take each point and you ask which bit of space is closest to that point rather than any other. And so you can partition space up into Voronoi cells. Yeah? So that Voronoi diagram is you keep the positions to be the positions of the particles that you observe, the late time positions, and you ask what are the volumes associated with each particle? What is the volume associated with each particle? Right? So the volumes are all different. Our initial conditions were that all the volumes were the same because everything was uniform. And so that means we're looking for a tiling of space where you have everything the same volume, but the positions are different. And so you're going to start from your Voronoi tessellation, and you're going to expand the small cells and shrink the big ones, and you're going to move the centers around as you do this. And so you're always keeping space totally tiled, and you'll end up moving them around to eventually have a perfectly uniform distribution. Yeah? And so here the optimal transport is that you moved the cell centers as little as possible to get this to work. And so the step forward is that, optimal transport has been used in many other fields, and so they've made this fast. And so Bruno has a super fast code for doing this semi-discrete optimal transport. Okay, so we used it. A quick aside, because it's too nice, this field. So Tata Steel is interested in this problem because if you take steel, it's a blend of metals, and they can image the blend of metals, and they can see the cells that are the different metals, and they can say, oh, but I like the metal to be less brittle and less bendy, so what were the grain sizes? And so what happens is the chemist mixes the stuff together, does the tests, and then tells the engineer, I want the cell sizes to be given by, whatever, this kind of thing. These are the cell sizes, these are the cell shapes, go make it, right? And then they go through this kind of analysis to figure out how to do this before they then melt the metal. Yeah? There are many places where this problem comes up. So we're going to use it just to do the reconstruction, right? So the BAO reconstruction. So the idea is that you start out with a bunch of particles at redshift 0, here, the size of the particles are the masses of the halos. And we want to map them back to the initial field. And so, the mass of halos came from bigger patches and the lower mass from smaller patches. It's periodic boundary conditions, and we're not, chopping them off so that you can actually see that the big guys are pretty big. Yeah. Okay. This is the technical rule for, if all these things were 0. So this would be the set of all Q around each xi, the set of all space around each particle that's closer to this particle than to any other particle. Okay. That would be the definition of the Voronoi tessellation, and then these are the weights that say, now I specify what the volumes should be. All right. So just a couple of quick checks. So you run the algorithm and you see what you reconstruct. And so, here's a massive halo, here's a low mass halo. The blue dots are the particles that make up the halo at late time. So that's what you start from. The black dots are the actual positions those particles started from. Looks like there's fewer because it's a grid and you're looking straight down the axis. So we could have shifted, rotated a little bit, but those are the initial positions. And the gray area is the reconstructed Laguerre cell from doing this optimal transport. Okay. And of course, this was done for a big simulation box, and we've just carved out one of the halos. Okay, so there's a few things to look out for. One thing to look out for is that the centers of the proto-halo and of the, the redshift 0 are offset. That's really what we're doing this for, right? Is to get rid of the BAO smearing is that offset between the center. But it's also true that the proto-halos, they have shapes, and the algorithm does a reasonable job of reconstructing the initial shapes of those blobs as well. So here's one where it's a little more dramatic. So this is the same halo, just 3 projections to show you that the center at late times can be quite offset from the center in the beginning. And the 2 crosses, one of them, the purple is the actual proto-halo center, and the green is the optimal transport reconstruction of its position. So it works pretty well. Okay. So that's you look by eye, it works pretty well. Now you'd like something quantitative, so you go out and measure statistic. And so here is the 2-point correlation function. Let's look on this side. I'll talk about these 2 in a second. So the nonlinear thing that you start out from is the gold, and linear theory is the black dashed, and the fact that the gold is different from the black dashed, that's the thing we're trying to reconstruct. And then let's look at the purple is the actual proto-halo centers. Yeah? So that's where those things started out initially. And the green is the reconstruction. And so we're supposed to look and say, oh yeah, the green looks like the purple. That's great, it's done a good job reconstructing. And a separate question will be, let's compare this to the linear theory shape. Because ultimately that's how we do cosmology, is by fitting a linear theory template to these shapes. Okay. The difference between these 2 panels is here each halo was weighted by its mass. Here each halo was not weighted by its mass. So this is a crude way of modeling galaxies. Number of galaxies is roughly proportional to halo mass, above some minimum. Okay. So it's to show you that it doesn't really matter. I mean, the purple and the green are in good agreement here, and they're in good agreement here. So you can have an HOD and this will still work. Although I've been talking about halos, galaxies are weighted halos, and it all works. Okay. So now to check the shape, let's again look at this guy. Okay. So there's the shape, which is linear theory, which is the black dot dash. There's the gold, so that's the mismatch we said we had to fit. And now I've rescaled the other curves. Okay? So the curves that I've rescaled, well, so so the first thing I've done is, these are the same shapes as before, but now I'm going to rescale the purple and the green. I'm going to rescale the purple and the green because these were objects whose number density was conserved. So we had them at redshift 0, and we asked where were they at some early time. And if you conserve number density, then their clustering is predetermined on large scale. And so the bias factor evolves in a known way. The bias factor becomes bias minus 1. Or if you want bias minus growth factor, and we're working in units where redshift 0 has growth factor 1, and redshift infinity has growth factor 0. Okay? And so what I've done to compare shapes, because it's harder to compare the gold with the purple and the green when they have different amplitudes, I've rescaled by the expected change in amplitude. So that's this B minus 1 factor that you see here. Right. So what you can see is that the purple and the green, they're in great agreement, but they're quite different from linear theory. The good news is they're sharper than linear theory, so it's a sharper peak to look for in the reconstructed data. But it's not the linear theory shape. And that's a kind of weird thing, because usually when people do reconstruction, they don't highlight the fact that the reconstruction may not return for you the initial shape, may not return to you linear theory. Okay? But you can see that it is returning to you the initial shape. The green and the purple are the same. So that means that the initial correlation functions of the bias tracers that we see are not given by linear theory. Okay? And that means that if you now fit a linear theory template to this shape, maybe you won't bias your distance estimate, because maybe the peak of here is the same as the peak of here is the same as the peak of here. But you will broaden your error bars because you're fitting a lousy model. And so there's gains to be had by understanding this. And so if I have time, I'll get into the energy peaks theory that explains this different shape. But so the main takeaway from this is that we're reaching the precision in data sets where we will start seeing that for biased tracers, the linear theory shape is not good enough. Okay? And it's not a failure of the reconstruction. It's a feature. Okay. All right. That was 2-point statistics. Then you can ask, how do you do with endpoint statistics? So I don't want to go through 3 and 4 and 5 points. So I just did the void distribution. I did the voids in 2 ways. There's you throw down randomly placed cells, or you take your favorite void finder, Subha or whatever, and you fit spherical voids or whatever shape voids, and you make a plot of the shape. Yeah. So let's look at one of these. I think so. One of these is more like the counts and cells guy, and the Eulerian, so the redshift 0 void distribution versus the initial one and the reconstructed one. You can't see the difference. Yeah, so that means, so there's a green and a gold, and they're sitting on top of each other. And so that means that the endpoint statistics, at least this particular combination of endpoint, comes out pretty well as well in the optimal transport reconstruction. Not terribly surprising, given that I showed you that actually the centers match pretty well, but it's nice to have a way to quantify that. Okay. All right, and this is sort of interesting because there's been recent work saying, if you want to use voids to constrain cosmology, then maybe you're better off doing it in the reconstructed field. And so this is to show you that, yeah, maybe that's true. You really do, at least this method does get you the initial void. Okay. All right. So I started the talk by saying it's interesting to do this because it's kind of less cosmology dependent, because you're reconstructing to an initial smooth field. And so you didn't specify anything about cosmology. You didn't say anything about bias. You didn't say anything about any cosmological parameters. So that's attractive. Yeah? It's not quite that simple, because this thing needs is it needs to reconstruct to an initial field. And if you're starting out from bias tracers, they did not come from a smooth field. They came from a clustered field. And so, but the algorithm is fast if you can give it a smooth field to start from. So that means you've got to make an estimate of the stuff that's not in your survey, if you want to take advantage of its speed. Okay. So there's two things then you need to assume. You need to know how much stuff you're missing. And so that means you've effectively made an assumption about omega matter. And then you need to decide if the stuff that's missing is clustered or not. And so if you're going to say it's clustered, you've effectively made an estimate, you've made an assumption about sigma 8. Okay? So you're not as cosmology free as you'd have liked. And so I'm going to go through a couple of slides where I say, then we, how cosmology dependent are we really in this method? Yeah. So the things that I showed you so far, this the mass that's below the survey limit that I'll call dust. It was a simulation, so I used the stuff from the simulation. So now I'm going to pretend it's as though it's real data. Now what would I do? Because I don't have that dust. Yeah. And so, so one thing you could do is you could just pretend the dust is unclustered. I throw down the right amount of dust, but uniformly at random, okay, and run the algorithm. And so if you do that, then so we did it for a few halo mass bins. The ones I was showing you before were the blue, were the red. But then I can take a higher mass sample or a lower mass sample and run the method. And so the dashed line is linear theory. And so now it reconstructs it to the linear theory shape with an amplitude that is that we can calculate. Okay, that's determined by the halo, by the masses here. So there are no free parameters in this, and it works reasonably well at getting the linear theory shape. But I've already argued that that's kind of the wrong shape to go back to. But if you're in the linear theory game, if what you were fitting was a linear theory template anyway, then this is saying you can assume uniform dust and do this. Okay. All right. You could say, I think the dust sort of sits around the halos, and so where there are more halos, there's also more dust. And so you can write down the sort of Wiener filter estimate, given the halos that I saw, where is the dust likely to be? So here's a model of doing that. Here's the Wiener filter estimate of where the dust should be, and that's where it actually was in the simulation. So this is the mass that is below halos above some mass limit, 10 to the 13. So low mass stuff. And you can see it's a sort of smeared out version of the actual thing. Wiener filter, so there was filtering, right? There was smoothing. That smoothing doesn't matter when you run the optimal transport and you look at the BAO feature. It doesn't matter really what you do. So we did the exact Wiener filter, and then we did, suppose I decided to smear everything in top hats, or I smeared everything in a shape that's analytic but close to the Wiener filter shape. Doesn't matter. The BAO is still fine. The differences appear on small scales. So if you're someone who you like to fit not just the BAO scale, but you want to fit the shape of the correlation function or of the power spectrum over a wide range of scales, you can do that down to like 20 or 30 megapascals and use the shape to tell you something about cosmology. But now to do this, to model a dust, you needed to assume how much dust as well as how it was clustered. Because to do the cross correlation, you measure with the Wiener filter, but then to put down the dust, you put a bias factor. Okay, so two quick pictures and then I'm done. This one shows you in the format that we usually use for showing redshift space distortions. This is the nonlinear field. This is the proto-halo field. And then these are the two models for the dust, the Wiener filter dust and the actual dust that actually traces the cosmic web from the particles. Yeah. To show you that this fuzzed out BAO has gotten tidier. So that's how tidy it can get, and this is how tidy it is from either of those reconstructions. And so now I've done this because I want to show you I can play the same game in redshift space distorted positions. And so now you can see that the redshift space distortions are much more severe. But the optimal transport can do the reconstructions there too. Yeah. And so One last thing about the redshift space. So because it's anisotropic, so you have distortions different along the line of sight compared to across. So the way you would do the optimal transport, you would start out with your data, which is, let's say it's in a cube. We can come back, or you can ask me later about what to do if it's not the plane parallel approximation. So you start out in a cube, you shrink along the line of sight direction, along the z-axis, by a factor that includes the peculiar velocity information, so 1 plus f. F is omega to the 0.6, more or less. So you've had to assume cosmology to do that. Then you run the algorithm, and then you shift back. Okay? So that's how you account for the redshift space distortions, the linear redshift space distortion. So if you do that, then you can measure the monopole and the quadrupole. We've been looking at the monopole already, so there's no surprises there. Here's the quadrupole. I don't show you the nonlinear quadrupole, which is down here. The nonlinear quadrupole is down here. It's been corrected, so it is back to something spherically symmetric on scales of order 50 megaparsecs and bigger. This simple linear theory 1 plus f scaling is no good on smaller scales. The green is the best you can do with the model for the dust. So the difference, the fact that green is not purple, is because linear theory velocities are not the full story. And this has only really reconstructed the linear theory velocity. The gold to the green is your model for the dust. And so if your model is bad, then you have a worse quadrupole. So this says there's gains to be had by modeling the dust better. So Shadab and Aseem have a Voronoi-based model for the dust. It would be nice to try and explore how that can be pushed through this analysis. Yeah. That will get you from the gold to the green. We need nonlinear physics to go from the green to the purple. We don't care for the BAO, but for if you want to use it for this. Okay. Sitting on here are dashed rather than solid curves. The dashed is, to play this game, I had to assume cosmology. I had to rescale everything. Supposing I said, forget it. I'm going to just take the positions as given, as observed. I'm going to forget about the fact that they're redshift space distorted. And I'm going to run the optimal transport as though it was in real space. The motivation here being that, I'm still constrained in the perpendicular to the line of sight. And maybe that's enough of a constraint that the fact that I've got a wrong distance along the line of sight by a little bit is not going to screw things up too badly. Yeah? And so the difference between the dashed and the green is doing the proper redshift space treatment and ignoring it totally. So there's like almost no gain to be had by caring in this for this optimal transport thing about the anisotropy. I mean, you care, you do the reconstruction, but you don't have to actually model it. Yeah. And a final check that that's true, we can just do the cross correlation between the initial proto-halo field and the reconstructed field. And this is what it is in real space. So R of 1 means they're tracing each other. So as you go to smaller scales, they fall off. But here in redshift space, so redshift space is worse than real space. But here in redshift space, it doesn't matter whether you did the full, you treated the anisotropy carefully or you just ignored it. Yeah, so the constraint that you're getting from the separations across the line of sight is pretty strong. But screwing up along the line of sight is not a big deal. Okay. Okay. And so that means you can probably do redshift space distortions without this extra assumption about F. This was the voids, and I should stop there. So optimal transport reconstructs the displacements pretty well. Better model for the dust will be big gains. And I didn't talk about the KSZ synergy, but if you're interested, you can ask. Thanks, guys.
We have time for a couple of questions. Yeah. It's like, I don't know which one of you to pick first, decide. Okay, Hamza, go first.
Thanks for the very nice talk. I had one question about the way your curves were on the very small scales. You had the green and yellow sort of, yeah. Is there a simple finger of God model which would work here? And is that possible to, because we tried something similar with simulations, student and Wiley Penn. We found in Lagrangian space, you can probably model it with a sigma. Is that interesting?
That would be interesting. So this dip, of course, is the halo exclusion. So it's the fact that they're a finite size, right? So it being negative is that they have some size. And so, you know, so one way I think of this is to say the correct answer is purple. And so how badly am I screwing up where the boundaries of halos are when I do the reconstruction? And then, of course, if I start with redshift space distorted positions, I'm going to screw that boundary up that much more. So it'd be great to be able to try and correct that.
I can go next. Okay, Arko, go.
Yeah, so for the uniform dust assumption, does that screw up the 1-point statistics somewhat more compared to the 2-point correlations?
So it depends in what sense you mean. So you want the 1-point PDF of the counts in cells. So that is,
yes,
it does slightly. So, but I haven't looked at, because I showed you P0, right? The void kind of thing. And so the reconstruction ends up being slightly bigger, but it's not as bad as Eulerian.
My question was more for the uniform dust where you're sort of not
I
using, is this from the?
No, so this was with the real dust, but if I made this, but having done with the uniform dust, it's not very different. Yeah, it is different. And so this one doesn't really show it either because this one has the other dust models, but not the uniform dust, right? But like you can see that as you go from real to redshift space, let's take this one, then you know you're broadening a little bit the PDF, but all of these are far from the nonlinear one. But I don't know what the nearest, you know, first, the second, or third nearest neighbor, what they would be.
Maybe one last question from Hector, and then we go.
So, so my question is about how this compares in terms of assumptions with the standard reconstruction. So, yeah, so the comparison between your method and the standard reconstruction method is essentially because of on the assumptions that you have to make, because eventually you have to assume bias, you have to assume growth factor. So, what's the actual?
You don't have to assume a growth factor here.
Huh?
In this one, you don't assume a growth factor. Correct. Exactly. Yeah. So in this one, you reconstruct you see the protohalo here, so you reconstruct the protohalos. So the gain is that you're doing a more accurate reconstruction. Whether that propagates to a more accurate distance constraint, I don't know, right? So we're doing that.
Sorry, so maybe this discussion can be taken offline. Thanks. Okay, let's thank Ravi again.